Hey everyone, in this video I'll introduce a commonly used gas law known as the combined gas law. So remember that so far we've already seen some other gas laws like Boyle's law, which says that for a sample of gas, its pressure times its volume initially will equal a new pressure and a new volume if one of those variables change. This is an inverse relationship as long as the temperature stays constant. Or you can do the same thing with Charles' law, which looks at volume and temperature. V1 over T1 equals V2 over T2, telling us that temperature and volume have a direct relationship if the pressure stays constant. What we didn't really say looking at these two gas laws though is which could you use if all three variables changed? In other words, what about if the temperature didn't stay constant? Then you can't use Boyle's law because the temperature is also changing and this relationship no longer exists. Or what about if the pressure was changing, then Charles' law no longer applies? And that's where the combined gas law comes in. This new gas law gives us a mathematical model that we can use to calculate changes in gas pressure, volume, and temperature when all three variables are changing. If we put Boyle's and Charles' law on the screen one last time and start to overlap these two gas laws, you'll see I'll sort of put the two volumes right on top of each other. We combine the two gas laws into one new equation that contains pressure, volume, and temperature. And that's the combined gas law. That statement and that equation are the key ideas for this video. Make sure you pause, take a moment, and write them down. In this equation, the subscripts of 1 indicate that those are the values before a change takes place, just like with Boyle's and Charles' law. The subscripts of 2 indicate those are the new pressure, volume, and temperature values after the change has taken place. You can use whatever units you want as long as they match on both sides, with the exception of temperature, which has to be entered as Kelvin. Here's a sample question where we can apply the combined gas law. This one talks about compressing a gas into a scuba tank. So first let's read it and label all the numbers we come across. It says a scuba tank is filled by compressing 4,000 liters, so my volume, at 25 degrees Celsius, so my temperature, and 1 atm, so my pressure. Notice I've got all three this time, P, V, and T. It says they're compressed into the tank at a new volume of 18 liters. So this volume is the new volume, that's a V2, which makes this the V1 and makes this T1 and P1. It goes on to say that during the compression, the temperature of the gas also increases to 36 degrees Celsius. So besides a new volume, I also have a new temperature. And that's what the combined gas law is all about. It's not only one variable that changes, they're all changing. And what I'm solving for is the pressure inside the tank, so we'll eventually end up with an answer for P2. So I went ahead and plugged all those variables that we just identified into the equation. Notice the units match on both sides, liters and liters, Kelvin and Kelvin. Also notice I went ahead and changed each of those Celsius temperatures into Kelvin by adding 273. The next step will be to start the algebra on this. I have to solve for P2. I'm going to recommend, just like we saw with our Charles' law problems, that the best way to deal with these fractions is to get rid of them by cross multiplying. So it's going to be this bottom times this top equals this top times this bottom. So after the cross multiplication step, we get a new equation that looks like this. Here's my P2 times 18, the top of the one fraction, now times the bottom of the other, 298, and same thing on the other side. Now there's a couple ways you could finish it from here. Some people prefer to multiply these numbers all together. I like to save all that math until the end. I want to get P2 all by itself on one side of this equation. And I can cancel out the 18 and the 298 sort of all at once by dividing by both of those numbers. On this side, that'll cancel out the 18, that'll cancel out the 298, and then just as we always do with any algebra problem, you have to do that same thing to both sides of the equation. So we're also going to divide by 18 and divide by 298 on the other side as well. Now you've just got all these numbers to plug into your calculator that will leave you with an answer for the new pressure. That answer, after a little bit of rounding, is 230. The units will be the same units as our P1, in this case ATMs or atmospheres. So the new pressure in the scuba tank will be 230 ATMs. And let's end the video with a second example that has a couple different issues to pay attention to when working with the combined gas law. This one says a 350 milliliter gas sample, so there's my volume, is at 275 Kelvin, there's a temperature and a pressure of 1.4 atm. The sample of gas is compressed until the pressure is 35 psi. Okay, so after the compression, it's 35 psi. That makes this my P2, which means 1.4 was my P1 and T1 and V1. Here's something interesting though. It says, and the temperature remains unchanged. So it doesn't give you what the T2 is, but if it's unchanged, that means the T2 is the same as the T1. So we know that the T2 is also 275 Kelvin. You can label that so you don't forget. So after plugging in all those variables into the combined gas law equation, everything looks pretty good, except you might notice an issue with my pressure units. 1.4 is in atms and 35 is in psi. So you can use either of those units, but they have to match. So usually what I'll do is change the psi into atmospheres. You could also change 1.4 atms into psi. It's totally up to you, but my preference is atmospheres for some reason. So let's first convert 35 psi into atms. To do that, we need our pressure conversion chart, and I've got that listed right up there. Remember, this is one simple conversion step using dimensional analysis, starting with the number and the unit I'm going to convert, in this case 35 psi. I want to cancel off psi, so I put it on the bottom of the fraction. That'll cancel bottom to top. And we're going to try to change that into atm. The conversion from the chart tells me that 1 atmosphere is equal to 14.7 psi. So 35 divided by 14.7 gives me the pressure, the P2, that will now be in atms. It comes out as 2.38. The important part now is the unit will match. So I have to take this 2.38 atmospheres, rewrite my expression, but plug it in for the 35 psi. So I just erased my original P2 in psi and plugged in the 2.38 atms. Now I can pick up pretty much where I left off with the last example by cross-multiplying to get rid of these fractions. And here's what it looks like after cross-multiplying. I've got the top of this fraction, 2.38 times V2, times the bottom of this one, 275, equals the 1.4 and the 350, the top of this fraction, times the bottom of the other one, 275. Remember, we're going to do this all in one step to get V2 by itself, dividing both sides of the equation by 2.38 to cancel off this part, and also by 275, which will cancel off this part, and then just do the same division on the other side of the equation. And when it's all said and done, we're left with only V2, my new volume. You might also notice that the 275s will cancel over here because the temperatures were the same. So technically the only math you're plugging in is those three numbers right there. This gives me a final rounded answer of 206. The units on the V2 will match the V1, in this case milliliters. So my final answer is 206 milliliters. And that wraps it up for this video on the combined gas law. Here's a brief summary.